In October 1942, the U.S. Navy faced a terrifying logistical reality. Across the Pacific Theater, they had exactly 0 undamaged aircraft carriers left to fight. The entire strategic weight of the conflict rested on the metallurgical integrity of a single, mortally wounded vessel, the USS Enterprise. While the ship steamed back toward combat, a team of 75 Seabees was out on deck, frantically welding steel plates and patching the flight deck while the ocean pitched beneath them. The Pacific War was secured in these moments by a massive display of raw industrial grit and an engineering framework specifically built to survive its own destruction. To understand how she stayed afloat, we have to look past the battle map and examine the actual ship. This is a forensic deconstruction of 2 directly opposing naval architectures. The 1942 campaigns reveal a specific mechanical discrepancy. Heavily armored, pristine Japanese carriers were routinely destroyed by minor bomb strikes, while the Enterprise absorbed devastating kinetic impacts and kept operating. The Japanese Navy went to war carrying a systemic architectural flaw hidden within their ship designs. Effective warship survival depends on architecture designed to actively manage its own internal failure. This diagram compares the hangar designs. The Japanese enclosed hangars protected aircraft from weather, but in combat, the enclosed walls trapped the bomb blast. Conversely, the American open-sided hangar allowed explosive overpressure to vent laterally out the sides, safely dissipating the pressure. Because the blast on the Japanese carriers had nowhere to go, the shockwave traveled internally. It instantly shattered bulkheads and ruptured their integral fuel tanks. By trying to protect their airplanes from rain, Japanese naval architects inadvertently turned their sovereign vessels into massive, self-contained pressure bombs. The initial bomb blast is rarely what sinks a carrier. The real danger is secondary fire fed by highly volatile aviation fuel vapors. A single stray spark ignited vapors aboard the USS Lexington, destroying a ship that had otherwise survived the battle. To solve this thermodynamic problem, machinist Oscar W. Myers developed a retrofit system for the Enterprise. His solution was to actively pump inert carbon dioxide gas directly through the ship's vulnerable fuel lines. This diagram shows the internal chemistry. Blue oxygen particles and orange fuel vapors are aggressively pushed out by a solid wave of gray CO2. Displacing the oxygen drops the atmospheric mixture of the confined pipe well below its explosive limit. This chemical intervention meant that even if a fuel pipe was sheared open by kinetic impact, there was absolutely no ambient oxygen available to feed a chain reaction fire. Beyond passive defenses, the Enterprise required a massive, active circulatory system to fight the heat. This blueprint shows the horizontal loop fire main, 2 continuous, interconnected circuits of pressurized seawater running along both the port and starboard sides. Japanese carriers relied on a vulnerable single main system. If a bomb severed that central pipe, teams lost all firefighting water. The American loop was built for redundancy. When struck, localized valves close, and water instantly reroutes down the starboard side. Applying this water in reality was a terrifying endeavor. Damage control crews had to secure bulkheads and operate heavy fog nozzles in total darkness, wading through rising water and choking on toxic smoke. It was this highly adaptable, redundant circulatory system that allowed the Enterprise to absorb massive amounts of thermodynamic heat and remain operational. The technical survival of the Enterprise was driven by a culture of mechanical improvisation. While Japanese naval doctrine remained rigid and top-down, American damage control crews relied on the hands-on troubleshooting skills common to a population raised on industrial and agrarian machinery. The Japanese built delicate glass swords, designed for perfect offensive strikes. The Americans built thermodynamic anvils, expecting to take a beating and planning meticulously for structural failure. The brutal battle scars on the Enterprise provided engineers with exact forensic data on how steel and fluid dynamics behaved under extreme kinetic stress. American shipyards took those perfected resilience designs and applied them to a staggering logistical feat, mass-producing the next generation of Essex-class fleet carriers. The internal systems of the Enterprise provided the blueprint for the next 24 Essex-class carriers, effectively shifting the balance of the Pacific through standardized, resilient engineering.